Hello students, welcome back. Today we will start with chapter number 4, that is principle of mathematical induction. Okay, there will be three types of sums in this chapter. The first, you need to prove about equality. Second, inequality means less than equal to or greater than equal to, less than greater than. And third, based on divisibility. Okay, so there are three types of sum that you have to solve on the basis of principle of mathematical induction. That is based on equality, based on inequality, and based on divisibility. Okay, now let's see how you have to prove for first principle of mathematical induction. Okay, what will be your first step? Your first step will be you have to prove P of 1 is true. Means an equation will be given and you have to use P of 1, take LHS and RHS. You have to prove that LHS is equal to RHS. Clear? Your second step will be assume P of K is true. Means in your second step you have to write as a let P of K is true. So in the given equation, wherever there is x or n, put the value as K. Okay, and third, as P of K is true, this must imply P of K plus 1 is true. Okay. So now see, P of 1 is true. You have to prove. P of K plus 1, you have to prove, but based on P of K is true. P of K is true. That implies P of K plus 1 is true. And the second step, P of K is true, that you have to assume. So if all these three are correct, then you can say that from principle of mathematical induction, P of n is true for every n belonging to n. Okay, clear? So let's start with exercise 6.1. You will get a clear idea at that next. But remember this. What is the first step? Prove P of 1 is true. Second, assume means let P of K is true. And third, P of K is true implies P of K plus 1 is true. So then from principle of mathematical induction, P of n will be true for every n belonging to n. Question number 1. Prove the following by using the principle of mathematical induction for all n belonging to n. So the first one is 1 plus 3 square plus dot 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 raised to 3 raised to n minus 1 equal to 3 raised to n minus 1 upon 2. So what was our first step? Our first step is we have to prove P of 1 is true. Okay, so let's say for P of 1. Okay, 1. So here we have to take first term. What is LHS? 1. If it was P of 2, that means 1 plus 3, 2 terms. P of 5 means till fifth term. Here P of 1 means till the value of n is 1. That is the first term here. So LHS is equal to 1. RHS, what is 3 raised to n? Instead of n, I will write down 1 minus 1 upon 2. 3 minus 1, 2, 2 by 2, that is equal to 1. So LHS is equal to RHS. So that means P of 1 is true. Okay, let's name this as 1. What was our second step? You have to assume P of K is true. So let P of K is true. So what will this mean? This will mean that 1 plus 3 plus 3 square dot 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 3 raised to Here it is n minus 1. I will use instead of n k. That is equal to 3 raised to k minus 1. Sorry, not here. Minus 1 upon 2. This were assume that p of k is true. That means this equation will be true. Okay. Now for p of k plus 1, what we have to prove? We have to prove p of k plus 1 is true. That means we have to prove 1 plus 3 plus 3 square up to 3 raised to k minus 1 equal to, sorry, not k minus 1, instead of n, I have to put k plus 1, so it will be k plus 1 minus 1, so this will get cancelled, so 3 raised to k equal to 3 raised to, instead of n I will put k plus 1 minus 1 upon 2. So I need to prove that this is true. So see what I am doing, I am taking LHS, right? See, that will be 1 plus 3 raised to 1 plus 3 square plus 3 cube plus 3 raised to 4, finally up to 3 raised to k. Now which will be the term before 3 raised to k? This will be 3 raised to k minus 1. Like see, if I extend this, 1 plus 3 plus 3 square plus 3 cube plus 3 raised to 4 plus 3 raised to 5 upon 3 raised to k. So see, term before 3 raised to 5, 5 minus 1, 4. Before that, 4 minus 1, 3. So before k, it will be k minus 1. Okay. So I had just written this term. Now see, what is this? Okay, if I take this is our equation 2, right? 1 plus 3 plus 3 square plus up to 3 raised to k minus 1. So what I will get? I will get LHS equal to, instead of this rate part which I had just circled, I can use 3 raised to k minus 1 upon 2 plus what is remaining? 3 raised to, okay, so this will be equal to, when I will take LCM, I will get 2 plus 3 raised to, sorry, 2 into 3 raised to k. Okay, clear? So see here, what I can get, 3 raised to k plus 2 into 3 raised to k. Okay, sorry, so this will be equal to 3 raised to k plus 2 into 3 raised to k means 3 into 3 raised to k. It's just like x plus 2x, 3x. So 3 raised to k plus 2 into 3 raised to k, 3 into 3 raised to k. Okay, I'm writing it here. 3 into 3 raised to k minus 1 as it is upon 2. Now 3 means 3 raised to 1. Same base, so 1 plus k, or I can write it down 3 raised to k plus 1 minus 1 upon 2. And this is our RHS. Therefore, P of k plus 1 is this is. And how we came to this result? By using equation 2 here, right? So from 1, 2 and 3, according to principle of mathematical induction, P of n is true for every n belonging to n. Clear? Okay. So this was about question number 1. So just note it down. Now let's move to the next, that is question number 2. Question number 2, you have to prove 1 cube plus 2 cube plus 3 cube up to n cube equal to n plus 1 by 2 whole square. Okay, so let's start with p of 1. For p of 1. Okay, so n cube, that is 1 cube, we have to take it till 1 cube. So LHS equal to 1 cube equal to 1. RHS 1, 1 plus 1 upon 2 whole square, that is equal to 1 into 2 by 2 whole square. 2 to get cancelled, 1 square is 1. Therefore LHS is equal to RHS, hence P of 1 is true. Okay, now let P of K be true. So what does that imply? 1 cube plus 2 cube plus 3 cube to n cube, that will be equal to, not n, k cube, that will be equal to k plus 1 upon 2. Okay, let's name this as 2. Now for p of k plus 1, we have to prove 1 cube plus 2 cube plus 3 cube up to, instead of n I will write down k plus 1, so k plus 1 cube, that is equal to, now here instead of n I can write down k plus 1, so k plus 1, instead of here n, k plus 1 plus 1, so it will be k plus 2, k plus 2 on 2 whole square. Okay, so now let's take LHS. Now see, you can use a shortcut here. I can write on here 1 cube plus 2 cube plus 3 cube up to k cube plus k plus 1 cube. I can arrange here one more term, k cube. Before k plus 1 cube, it will be k cube. And that is equal to this. So every time I can use the shortcut, I can write on the RHS of this, that is k plus 1 upon 2 whole square plus this one. Okay, because this will be 1 cube plus 2 cube plus 3 cube up to k cube, that is this, plus k plus 1 cube. Okay, so let's solve it. What is common here? K plus 1 square and k plus 1 cube. So I will take k plus 1 square common here, k plus 1 square common, so this will be equal to k plus 1 whole square common. What is remaining? K square upon 2 square, that is 4, plus here k plus 1 cube is there, from that square I have taken common, so remaining is k plus 1. Okay, so now let's take LCM. This will be equal to k plus 1 whole square, k square plus 4k plus 4 into 1, 4 upon 4. Now see, this is the formula a square plus 2ab plus b square. This is the formula for k plus 1, sorry, k plus 2 whole square. Okay, so what I will get? K plus 1 whole square. In numerator this, k plus 2 whole square upon 4. So when I take square outside, it will be k plus 1, k plus 2 upon 2 whole square, and this is equal to RHS. So this is 3. So from 1, 2 and 3, according to principle of mathematical induction, P of n is true for every n belonging to n. Here, so this was about question number 2. Just note it down. Now let's go to the next, that is question number 3. Question number 3, 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 up to 1 upon 1 plus 2 plus 3 plus up to n equal to 2n upon n plus 1. Okay, so now let's start for p of 1. Okay, n equal to 1. So I need to take denominator till 1. 1 upon 1, that is LHS equal to 1. RHS 2 into n means 2 into 1 upon 1 plus 1. I can write directly 2. So to get cancelled, that is equal to 1. Therefore, E of 1 is true. Let's name this as 1. Okay. Now, second step, let's assume P of K is true. What will this imply? 1 plus 1 upon 1 plus 2. 1 upon 1 plus 2 plus 3 plus K, that will be equal to 2K upon K plus 1. Okay, let's name this as 2. Now, for P of K plus 1, we have to prove 1 plus 1 upon 1 plus 2 to 1 plus 2 plus 3 up to, it's not n, instead of n I will put k plus 1, that is equal to 2n. So 2 into k plus 1, that will be equal to 2k plus 2. Okay, so 2k plus 2, and in denominator it's k plus 1 plus 1. Instead of n, I am putting k plus 1. So it will be k plus 2 upon k plus 2. So I need to prove this. Okay. Now let's take LHS. We will take shortcut. This term will be as it is, like plus 1 upon 1 plus 2 plus 3 up to k plus 1. And before that it will be 1 upon 1 plus 2 up to 1 upon 1 plus 2 plus 3 up to k, this. So instead of that I will write down 2k upon k plus 1. Okay. So now LHS will be equal to 2k upon k plus 1 plus 1 upon. Now see, this is 1 plus 2 plus 3 up to k plus 1. If it is like this, if it was 1 plus 2 plus 3 up to n, then you are studying sequence and series. That is, this will be equal to n plus 1 by 2. Summation of n natural number, that is equal to n plus 1 by 2. But here it is k plus 1. So instead of n, I will use k plus 1. So I can write down this as, instead of n, k plus 1. n plus 1 means k plus 1 plus 1, k plus 2 upon 2. Okay, and that is in denominator. So k plus 1, k plus 2 upon 2 means into 2 here. Okay, so now what I can take common? I can take common 2 upon k plus 1. Okay, so I have just taken here 2 and k plus 1, 2 and k plus 1. So what is remaining? K plus 2 upon k plus 2. Clear? So this will be equal to k plus 1, k plus 2 into k square plus 2k, and this plus 2. I have taken LCM k plus 2. Okay. Now k square plus 2k plus 2, when I will factorize, I can split middle term. That will be equal to k plus 1 whole square. Without splitting, I know this is a plus b whole square. 1 representing k plus 1 whole square upon k plus 2. K plus 1 and this square gets cancelled. So 2 into k plus 1, 2k plus 2 upon k plus 2. And this is equal to RHS. Here, so from 1, 2 and 3, from the principle of mathematical induction, P of n is true for every n belonging to n. Here, now remember one more shortcut. When there is equation like this, and we need to factorize it. Okay, just remember what we I want k plus 2 in the denominator, so this will be as it is. I don't want this k plus 1, right? So one of the factor will be k plus 1, so it gets cancelled. Okay, you can use this thing. Okay, so this was about question number 3. So just note it down. Here there is a mistake. Here it will be 1. And here also it will be 1 because I have taken 2 common. Okay, and if it is k square plus 2k plus 1, then what will it will be k plus 1 whole square. Okay, so just make a note of this mistake. Now let's move to the next, that is question number 4. Question number 4, 1 into 2 into 3 plus 2 into 3 into 4 up to n into n plus 1 into n plus 2. You have to prove this is equal to n plus 1, n plus 2, n plus 3 by 4. Okay, so now let's start with p of 1. For p of 1, so when I take n equal to 1, 1 plus 1 2, 1 plus 2 3. I need to carry on this when I get till I get 1 2 and 3. That is the first term only. 1 into 2 into 3, that is equal to 6. This is LHS. RHS n means 1. 1 plus 1 2. N plus 2, that is 1 plus 2 3. N plus 3, that is 1 plus 3 4. Upon 4, this is also equal to 6. Therefore, P of n is true. Let's name this as 1. Now, for P of k, sorry, we need to assume P of k is true, right? So let P of k be true. So what will that imply? 1 into 2 into 3. 2 into 3 into 4. n n plus 1 n plus 2 will be equal, not n, I need to write down k. Instead of n, k plus 1, k plus 2. This will be equal to k plus 1, k plus 2, k plus 3 upon 4. Okay, so this is about p of k. Now for p of k plus 1, we have to prove 1 into 2 into 3, 2 into 3 into 4 up to, instead of n, k plus 1. Instead of n plus 1, k plus 1 plus 1, k plus 2. And instead of n plus 2, k plus 1 plus 2, k plus 3. This is equal to, now here instead of this n, I will write down k plus 1. Instead of this n plus 1, k plus 1 plus 1, k plus 2, similarly k plus 3 and k plus 4 upon 4. Okay, so we need to prove this. So let's take LHS. We will take shortcut. This will be the last one that will be remaining here. But before that, it will be k plus 1, k plus 2. So instead of that, I will write down k plus 1, k plus 2, k plus 3 upon 4. Plus, here I will get this k plus 1, k plus 2, k plus 3. This term. K plus 2, so see, I can take here common k plus 1, k plus 2, k plus 3. So what I will do, I will take common k plus 1, k plus 2, k plus 3. So what is remaining here? K by 4 plus, nothing is remaining, so I will write down 1. So this will be k plus 1, k plus 2, k plus 3. When I take LCM here will be k plus 1 into 4, 4 upon 4. And this is equal to RHS. Let's name this as third. So from 1, 2 and 3 according to principle of mathematical induction, P of n is true for every n belonging to n. Clear? So this was about question number 4. So just note it down. Okay, students. So that's it for today. Today we have completed the first 4 questions of exercise 4.1. In our next video, we'll continue with this exercise from question number 5. Thank you.